There we go. Hello. He's here.
Well, my laptop crashed like right at like 1:58.
Ah,
And I'm like,
of course.
"What timing? I've been using it the whole morning. Let's see. There we go.
All right, you're here. This is the crowd we've got. You know.
Hello, crowd.
Got some people. Got some donuts.
I'll just put a donut in my mailbox.
I'll do that. If you got some
All right.
extras. All right, so I'm hoping you'll be able to see that. Christian's gonna intro us, and then I'll switch over to my other laptop here with the slides.
Okay, everybody here, that's great. So, hello everyone, my name is Christian Eckert, and I'm the lucky guy being the thesis advisor of Chase, who had a fantastic idea for his master thesis, and I think successfully widened the envelope of possibilities in virtual reality. And I will not go more into details because Chase will have all the opportunities for doing so. Let me just briefly tell you the overall plan, what we are doing today. So this is a thesis defense, it's public. What we are doing is I will give the word to Chase in a minute. And then after his defense, the word goes back to me. I will first ask the committee members, April and Michael, for any questions. After that, I will ask anyone else in the room or online if you have questions. And after that, I will go into a breakout room with the committee, and we will deliberate whether or not Chase has passed. Then we will invite Chase to this room and only him. We will tell him the results, and then we will invite everybody again into the Zoom, into the main Zoom, or everybody who is in the room. And then, well, you hopefully can celebrate.
Yeah.
Okay. Okay, so
Cool.
Chase, you ready?
Yeah.
Go for it.
Thank you. I'm just going to switch laptops here for the screen. Like Christian mentioned, I guess let's just keep interjections until the end. We'll have the committee ask questions, and then you guys can open up for questions if you have any. See that? Yep. All right. Hello, everyone. I'm Chase VanderZwan, if you don't know me. I'm going to be defending my thesis today, my research that I've been doing over the last 6 to 8 months. So I'm just going to get right into it. Here's kind of an overview of what we'll be going over. I'm going to have an introduction, kind of like the motivation, the context of what my research is all about. On the background, I'm going to have some definitions, some terms, and some framework that the rest of the presentation will be about. Methodology, I have 2 algorithms that I've coined NTA and CPL. I'll go into detail about what those do and the purpose. And then we have some results slides with some graphs to kind of go over how these algorithms performed, and some concluding thoughts at the end. So going right into the context, what is this all about? So essentially, this kind of all stemmed from an internship last summer. I worked in Florida at this great company, and had the opportunity to work in virtual reality, and kind of just open this can of worms of interest about how can we use VR to create immersive experiences. Notably, one of the restrictions that I'm going to be focusing on in VR immersion is the play area. So you see this image here, kind of has, any VR application, you're going to have to kind of define a play area so you don't run into couches or just, stay in your defined zone. And so this can kind of be a limitation on immersion, and I thought this would be an interesting, part of VR to look into. Oh, wrong one. So there's a couple papers on movement types to kind of navigate a VR experience. There's a lot of different ways people are experimenting with. Here are 4 common ones. There's motion-based. I have a couple of game examples here. This top one is Gorilla Tag, which is a hilarious game where you're using your arms to kind of actually like move. You're kind of stationary, but you're moving your arms. And so a lot of people found this to be immersive, but it can be tiresome. There's other similar ones like just like jogging in place. The next one is controller based. This is really familiar for a lot of people. If you've used console or just other platforms other than VR, This is a common mode. You're just using a joystick to move around. A lot of people did find that this kind of breaks your immersion because you are stationary while the virtual world is kind of moving around you. So that can create a lot of nausea from that disconnect. Another one is teleportation. This is really common in first-party applications. It's basically you point and then wherever you're kind of indicating, you snap to. Very similar to controller in its downsides, but still very common. And finally, room scale. If you've ever heard of Super Hot or similar games, you're kind of they set you in this area and you can kind of actually walk around and grab stuff. So a lot of people found this to be immersive, but there is a limited range of motion. And so one more movement type, some alternatives built kind of specifically for VR is redirective walking. This can be kind of complicated and not intuitive, but essentially what it does is it does use room scale movement. But in addition to that, to kind of overcome the restrictions of the play area, it uses something called saccades, which is kind of like you have random eye movements whenever you're just looking. And during those random movements in your eyes, the virtual world will actually kind of shift around your headset. And so it's this really trippy little thing that happens. Essentially, in the virtual world, you walk straight, but in real life, you're kind of making this curve. It feels like you have infinite space to work with. In addition, like paired with movement types, you have transitions. So when you're navigating a virtual world, you can move your player, but also you can kind of move the world to you. So one example would be non-Euclidean geometry, which is its own separate thing, but it kind of what you can do is stretch space. So you can make like a little tiny hallway where you're only walking a couple of meters, but in reality, you've kind of moved way further than you'd expect. Transformation is kind of just, you go from one place to another and it kind of just unfolds around you. Portal and orb are kind of the same thing. You can kind of see where you're going. That's why a lot of people like this method. It's not as nauseating, so you can kind of see where you'll go. And so these are two common techniques. You'll see bolded as portal. That's the type of combo you're focusing on. In total, I'm going to be basically proposing a game type that uses room scale movement, and to overcome the limitations, we use portals to get around everywhere. So with this game type, there are some challenges, and that's where the algorithms will come into place to overcome this limitation. And so I kind of have this demonstration here. If you take our Guardian image I've been showing and kind of just create it into this blue square, we place the player. This is like in the real world. We have like two areas somewhere in the virtual world. This is kind of just a representation of where the player would exist at that time. If we walk forward and we walk through the portal, obviously the player teleports virtually, but humans cannot do that. So we just keep walking straight. And this basically creates a disconnect. So right here, initially, we kind of had a one-to-one virtual to real. But after we portal, there's kind of a disconnect. And that might not be intuitive at first. But if you kind of just play it out, if you walk forward, if you're in game, you're like, hey, I can keep walking. So you might be surprised when you run into a wall. And so the solution, or part of the feedback that my algorithms provide, is determining for any set of interactions, what part of this area in the virtual world is going to be reachable. And so one example could be you find that these tiles are not reachable by the player. So you kind of just make them like fall out, maybe put lava, something of the sort. And so the player can be confident that whatever land they see, like they can walk to, and they don't have to think about, is there a disconnect? Am I going to run to a wall? And so forth. In short, kind of a one sentence overview of what the goal is kind of just an in-depth research on creating infinite walking while using room scale movement and portals to define this new game type. All right. Going into some definitions, just as a foundation, I basically assumed the player region to be kind of a square shape. And we have a common living room size is 8 by 8 feet. In practice, this could be anything, 6 by 6 feet. You could kind of alter this entire algorithm, this entire research to work with whatever size. But just to kind of go over some specific scenarios, I've defined it to be exactly 8 by 8 feet. So you have a bunch of like 2 by 2 feet tiles here. So here's kind of like a high level, what do the two algorithms do? What is kind of the goal? And so this first one, NTA, essentially what it does is it tries to find it tries to find this interaction of what is reachable. So you see like these green tiles here. In this region, maybe only a quarter of the space is actually reachable by the player. But with a certain set of portals, maybe that region will recenter the player kind of. The next builds off of this algorithm. So it uses the information provided by NTA and kind of finds compatible locations. So in this example, say you want, as a developer, you just want to build some weird, wacky shape or something else, and you have a bunch of kind of platforms throughout your world, but you don't care where the player, what portions of the grids are available to the player. But at this point in the game, I want this area to be for sure reachable. Essentially, it'll find, hey, where should the player portal to, so that when they go here, we know for sure that those tiles are available. And for exact reasons why I'll get into later. So for some definitions, I've just defined a grid to basically be 1 through 16, just in that order, just if I refer to any tile names. We kind of have like a source and destination grid. So a source grid will kind of have a blue portal, and I'll always kind of point out, you can't tell, and then the destination will have an orange, so you kind of, source, you're exiting the grid, and then you're entering the destination. Accompanied with this research, I kind of built a tech demo in virtual reality and Unity. And so this game could use these algorithms in real time. And you'll see a lot of these visuals that kind of show, we have this grid notation, but what does it look kind of practically? There's going to be a legend here just for terms that come by, so if you need to reference it. 2 final terms to note is I've coined the forward tile. This is essentially, if you have a portal, what's the tile I'll be at once I exit? This is really important just for an alignment process. Likewise, just where the portal exists is the portal tile. All right, so for the first algorithm, NTA, the first step of NTA is grid alignment. And so I kind of have a practical demonstration of just to prove that the alignment process, like what it does. So if you take 2 just random layouts, say the player offset is kind of like this, you got 2 portals. This is what it looks like. Also, just one more thing to note, you'll see wherever I have portals, I kind of have like these 4, like this pillar shaped thing. I've just decided to use as my framework. Wherever there's a portal, we use a pillar. And so say we have this layout. Let's say the player is right here, so right in front of this portal. And I've kind of created like a ghost version of where it kind of like represents where they would be. And you'll see why in a second. If we kind of just play this out, right, the player portals that keep walking over, the relationship between these 2 might not be obvious, which is why we do the alignment. So if I back it up here, the first step, so the idea is that we're basically, these 2 portals exist on an edge, and there's like a virtual spatial gap between them. So we just close that gap. So it's just like a direct, you're going from one place to another. So the first step is it looks to make sure these portals are facing opposite directions. So right now they're both facing south, so we'll make this one face north. And then we have to translate it. So this has to go up 1 and then over. And so then you kind of get something that looks like this. If you have kind of both grids over top of each other, you have this one here, this one being flipped. And then if we walk through, I don't know what animation to play. If we walk through, you can kind of see like this 1-to-1 relationship between the 2. And this is just reinforcing, if you kind of don't want to think about the math of how that works, just look to overlap a portal and a forward and a forward and a portal. And that's just kind of what the notation happens to end up looking like. So let's go into examples of the algorithm running. Here's a scenario that I've coined like equivalent grids. So if you'll see like the portal and the forward are kind of flipped here, but they're at the same location. And so if we follow our grid alignment, it's kind of like a 1-to-1, right? So there's a 0 grid offset and all the tiles are going to be reachable. And so this one of the results of this is you have something that I've called compatible locations. So if you take any source grid, right, any portal location at all, so I'm just using tile 6 for an example right now. There's going to be 4 compatible locations. The first is the one I just showed, but we have the 90-degree rotation, 180, and 270, which kind of just makes sense if you kind of do this overlay action here. You'll see during the grid alignment, each one of these 4 compatible locations will kind of have like this 1-to-1 relationship. If you have a non-compatible location, so again, this is kind of the same example. We know from the previous example that the compatible location is kind of here, but we are now over 1 and down 1. So it's kind of this offset. And that offset will become apparent when we do our grid alignment process. You'll see that the play area is now also offset by the same amount between the compatible location that we've actually used. And this is the flipped orientation, but you'll notice like these 9 tiles render, actually, no, it's not flipped. The top row in the left column are now unreachable. And so in game, kind of that reflects. This is just another scenario showing with a rotation. If we do our alignment process, you're left with kind of this one column that's not reachable. And so this section talks about play area offsets, basically just to demonstrate that this algorithm can do any number of iterations. So I've showed 2 portals, but what if we go from here to here? And now this one's different, and we go and keep going on. So show 3 grids right now, just these 2. We do our normal alignment process. We're left with 9 tiles that we can reach. This play area offset kind of now related to grid 2. We remove the overlap. You can see what that kind of looks like. And now if we kind of just flip this notation back into source notation, because we're now going to be going from here to the next one, bring in the grid 3. We follow the same grid alignment process as just showing it in game again. Same alignment process. And it will successfully determine the number of tiles available. So any process I've shown for 2 grids, you can basically just keep doing this for however long you need to go. This is just an overview of what we did. So grid 1, we ported to grid 2, we're left with kind of 9, and then grid 3 kind of brought us back to the center. We're going to leave questions till the end, sorry. So this is kind of the nitty-gritty of the code, which may or may not be interest to some of you, but essentially what the code needs to do is, even though visually we can see what the player offset does, right, when we do this rotation, how do we keep track of it when there's a bunch of grids going on? So essentially what you want to do is you take your source and just do the same transformations, right? So if we're rotating the source grid twice, you just need to rotate this player offset. You might not be able to read this, but it's saying, if we have an offset -1, -1, the clockwise rotation will become 1, -1, and then 1, 1. If we do our alignment process, the grid offset is off by 1 in each direction. And so that results in the play area kind of overlapping with the second grid. And so it takes this calculation plus the offset to become player offset, which is pretty intuitive, just that's how the math works. Again, this is kind of the nitty-gritty, but the calculation for the number of tiles just takes all 16 tiles, says it's called a bitmap, but all it's saying is yes or no, is it reachable? And once we figure out what tiles are not reachable, you kind of just count what is yes, what is remaining. And I've noted here optionally, you can also, if you want to include like obstacles, say you have trees or even just the portal walls themselves, you can subtract that from your calculation as well if you want. So this is going into the methodology of the second algorithm, CPL. The first thing I want to describe is the custom game element. And so just for an example, I can have a 1x2 grid here. You have a portal and then this tile kind of moves. And so what the algorithm will do, it'll take whatever kind of structure you give it and transform it into the base format. So it's 1x2, we transform it into a 4x4. We just set all these extra tiles to be air, right? And so whenever the code can now use all the algorithms we talked about before. And then additionally, I have kind of these stars here. And that's just to denote required tiles. Like you remember from the overview, I talked about how this algorithm tries to confirm that these starred locations will be walkable. This is just showing like if we had a moving thing, what would be required on the next thing. It's not terribly important. So this is it in action. This is an example of CPL. It requires a buffer grid. So this one, if you're going from here to here, you need a buffer grid that's empty. This is where we're going to place the portal. So let's say, you've been playing, you're walking around the world, you end up on this grid with this offset. And in 2 grids, you're going to have some required tiles. Essentially what it'll do is it'll pick a random location. So out of all 16, north, south, south, east, west, just chooses a random one. Says, all right, let's just try this. We use the NTA grid alignment process, determines what's reachable. And then kind of basically just check if these tiles are going to be in your play area. If we do the alignment of this buffer grid to our target, might be able to see that only one of the 3 tiles that we've marked as required are inside this play area. So that location would fail. Go back to square one. We choose another random location. You'll see this, it shows the west side and the east side here of another random tile. Alignment process, we determine what is walkable. We see the result. We align to our target. And in this case, all of the tiles that we've marked as, hey, we want the player to for sure be able to walk here are within the play area, meaning that we have a success. So here are some of the results of both algorithms, starting with NTA. And all of my examples, I kind of showed one specific location to another specific location. But in total, the algorithm will take 2 grids, right? If you have a pillar here and a pillar here, it'll find the NTA for every single combination. So in this example, we have this one has 4 options, right? This one has 2. We're left with 8 total combinations. And the first observation is that your number of tiles available does vary. It's not just, if this was, no matter what we did, the player can reach all 12 tiles, then this would be very interesting. But it does vary. And so we can see, you can do some stuff with this information, right? Let's say that we want to prioritize as much play area as possible. One thing you can do with this is say, hey, let's remove all of the data values with like the lowest NTA. And in this case, that's the north and east space would remove these values. And so we say, hey, if the player decides to do anything with these 4 remaining options, we know that at least like half of the area will be reachable. So that's kind of like an example of what you might do with the results. This is another example. You'll notice that in this case, we have 16 possible combinations of portals. And again, this just confirms compatible locations are useful if you're trying to redirect the player back into the center of the play area. So out of these 16 combinations, I've just chosen one that has 16. This is kind of a recap, but if you take that specific scenario and do the alignment, you'll see that the whole region is reachable. One final thing about NTA, this is just showing if it's down the line, we're at a point where there's an offset. it can still find the calculation for everything. And I want to note about, again, redirecting towards the center. There's just this kind of interesting interaction with compatible locations. If we take this example right here, right, north and north, you'll see if we do the first step of NTA is rotating, you'd expect the compatible location to be here, right? It's kind of the same tile but flipped. Right, so if I put that there, this is the default compatible location. However, obviously, again, this is pretty intuitive once you see it, but the player is kind of offset, right? And so the compatible location is also going to be offset, which is why this location here, 13, provides us a perfect 16 instead of the default location. And so I think this might be the most important slide if you take anything away from this presentation. It's what is the generalization of NTA? What I found is that any pillar tile basically has one of three types. It can either be a corner, an edge, or a middle. A corner will give you 2 possible, an edge will give you 3, and the middle will give you 4 possible portal locations, right? And so what that means is there's 6 types of portal combinations, right? You portal from a corner to a corner to an edge, etc. And so you know, the nitty-gritty I was showing of the NTA values, maybe that's too nuanced. You don't want to go through every specific little scenario. For some generalized results, and I know this might be hard to see on Zoom, but you can kind of just take the types, right? You can say, I'll go to a specific example first, but or later. But first, I want to show that no matter what combination you do, so if you go from a corner to a middle, corner to an edge, no matter what you do, none of the options will provide an NTA of 0, which is just basically saying, even if you kind of just build this randomly without any of the feedback, the player's not going to end up in a situation where they're kind of like soft locked. There's nowhere to go. The next observation is, again, you can kind of prioritize low or high NTA. So maybe if you have a puzzle game and you want to kind of restrict their options, blue represents corner to corner, so maybe use a bunch of corner tiles. Or up here, middle, one of the options is 16. And finally here, another thing you can kind of look at is if you were to only use like middle combinations, right? Your lowest option would be 6 NTA. And in other words, if you only use middle pillars in your whole entire game, what is that, like a third of the grid will always be breachable, if not the whole thing, 60. So the second algorithm, here's some of the results I found from that. If you remember, this just tries a bunch of random locations on this buffer grid to find a location. Again, you might not be able to see the exact numbers here on Zoom, but essentially this is just showing how long it took to find a solution. And so this blue is if we go in order from tile 1 to 16, it takes significantly longer. Like this is 50 tries, this is 100 tries. Whereas if you just try a bunch of random combinations, it finishes in under 10 attempts. And there's a reason why this pattern exists. You'll see that like every time it finishes right here, it finishes exactly 47 tries or exactly 97 tries. And this is because the whether or not a random location works is entirely dependent on it's entirely dependent on the source, right? So if we take a pillar tile here, pillar on tile 6, and we're testing north, right? So in order, it would take north and then try every single possible combination, and then east, every single possible combination. So if we try north, I'm just going to show like a bunch of different random locations with north. And every single possible I didn't show like there's like 200 combinations here, but every single combination will have the exact same relationship. So in this case, one of the tiles is breachable and it has like the same exact relationship with the player offset. Whereas if we try, let's say the west face, I only show one random location, but this will work for every single possible spot here. It'll always have this relationship. And so if we look back at this graph, it's essentially saying, oh, I've tried north with everything, and then I tried south and I found one immediately. Again, this kind of just shows that like testing random locations is the best way to do that algorithm. So wrapping up, these are some closing thoughts I have about the research done here. So these algorithms can kind of provide interesting and useful feedback about this game type that I've defined that uses room scale, movement, and portaling. You can prioritize large or small range of freedom by determining what's going to be reachable. You can kind of define, I want a game with a bunch, like the player always has a bunch of space to work with, or small if you have like a puzzle game. And then another thing is the CPL algorithm can be used to automate pillar tile placement. What I mean by this point, what I want to point out is that basically, again, I'm going to use like a puzzle example. Let's say we have a game where the first like half, you have like a bunch of enemies and you're just fighting. It doesn't really matter what this looks like. We just have a bunch of random stuff here. But then towards the middle of the game, we have a puzzle, and let's say you have a key card and like a button that for sure the player needs to be able to reach. We can kind of just plug this algorithm in, and we can have like this fighting area, but also be sure that the player will be able to use a puzzle elements. Last thing is just future work. How can you build off of this research? I see there's two kind of main ways to build off of it. The first is to lift the constraints. So use the same game type, but maybe instead of using a grid, you use just a different shape. Another thing could be instead of pillars, you kind of use a different shape. I kind of just showed a hexagon here. Another example could be using different transitions. So if you remember like non-Euclidean, how does that affect this relationship of the play area and what's reachable? Finally, you could kind of just build off of the same framework, like with the grids, but maybe you try different custom game elements, maybe like an elevator thing. How does that affect stuff? And then also, there's more like nuanced findings you can have. So for example, I showed you these three types, but there is a fourth. Once you have an offset, you can actually have a pillar that only has one possible location. And so that kind of just brings out a whole another set of relationships. And you can kind of research on what those relationships are. But that is everything. Here's some references. Thanks.
Thank you. Congratulations.
Thanks. You got, yeah, you got on that.
Okay, Chase. First, I'm asking the committee members, April and Michael, do you have any questions for Chase thesis defense?
April, you can go first if you want.
Sure, yeah. I was curious, as my experience with VR is always the difference in everyone's setups. And so I'm curious to know how hard is this to adapt to a smaller or larger play area? Like, is that just you shrink the tiles, or are you thinking about like a 3x3 or a 5x5 tiles?
Yeah, I think I've kind of done some research on, what is the one-to-one, like basically how you'd be limited by how big a person is. So you can't make a tile smaller than a person because they wouldn't be able to portal. Well, unless you go sideways, I guess. So you could shrink the 4x4 in those cases, but if it's really small, like you have 5 feet, yeah, you'd have to use a smaller grid size. That would just limit kind of your freedom, right? You would have less types of things you can do with the game.
But the number of tiles, like the algorithm still works if you have like a 5x5 square. Like, can you talk a little bit more? Because you said at the beginning it's extensible to other sizes, but yeah, what goes into those other sizes?
So the main thing would you would have to add like it's a lot of the algorithm depends on finding like the row and column of a tile, right? So a lot of it's based off like if you remember the forward and portal term, finding like the location of that is very important. And so if you have a 5x5, basically you'd have to just change the algorithm to say, you know, the index is now to a 5x5. So for example, if your index is 6 on a 5x5, that row and column would be completely different. So that's the main difference that you have to change. Is really like think about the indices.
Okay, thank you.
So I think I'm at a little bit of a disadvantage because I didn't get to read your paper. So I'm trying to imagine all this as you go through. I will read the paper, but I was driving to LA yesterday. So maybe you can help me with one thing before I ask some additional questions is in my game, if I wanted to walk the equivalent of 10 squares forward, in my actual space, I'd probably be walking in a square.
Yeah.
I would walk forward, see a portal, or a portal would be to my right. So I would turn, go through that portal, but I'm making forward progress.
Right, exactly. Yeah.
Okay.
Yeah. Yeah.
That definitely helps. Were you able to build, or I guess it would require first building a prototype of any type of activity and do user testing, how they reacted to this type of movement and how it compares to the other forms that you listed at the beginning, controller, which I'll just hurl like every time I'm with the controller movement.
Yeah.
Yeah.
Yeah. Well, I didn't do any user testing myself on how people reacted, but kind of my interpretation of how people would react is with room scale movement, kind of just in general. People find it to be less nauseating. And then portals, like people were saying, you know, if I can see, if you can see through the portal perfectly, you can see where am I going to go. People react positively to that, right? Because you can see everything that's going to happen versus controller where everything's moving around you. So that's kind of my only insight into how people would react.
Okay, so that's where the illusion that I'm walking forward is through the portal. I can see the forward view.
Yeah.
And even if I have to turn and go this way, I'm seeing the forward direction going through. Okay, that helps me build a mental model of what's going on.
Yeah.
So in the game space, you're like, oh, I want to make sure I can get to these target locations. I believe
Right.
I'm understanding it right. Do those have to be contiguous?
That's a great question. I don't think so. I think, you know, in my testing, I claim that it will always find a solution. But that testing was with contiguous required or whatever you want to call it, tiles. So I think there, if you didn't do contiguous, right, you just had like, you know, have a couple puzzle elements that are spaced around. I think the only thing would be that there are some situations where you wouldn't find a solution, if that makes sense.
Mm-hmm. Do you think that, so let me back up. You're envisioning this is a tool for a game developer. And so as a game developer, I'm using your algorithms and I get back no solution. What in your documentation for this API, would you be like, oh, here's what I recommend? Like just black out the world and redraw it so there are solutions, or you know, like what would you recommend to a developer when they get the response no solution?
I think, well, I'd have to add to the algorithm because I'm thinking now you basically just need probably 2 buffer grids, right? So my code kind of just tries for 1 buffer grid, but I think if you had 2, you know, there's a lot more you have to try a bunch of, there'd be a lot more calculations to try. But in my head, that would make sense, right? Because you have 2 tries to kind of reorient the player into an area. Otherwise, you could probably just return like what is reachable, right? And so say, oh, there's no solution, but if you move your button left, like it'll be, you know, it'll work with these locations or whatever.
May I moderate here a bit because I think there was a miscommunication.
Okay.
Chase is reacting to a question in his mind. It's a complete dynamic environment. But this algorithm could give the tools for developers, so the developers are creating a world which is constrained, but is following these rules. If this makes sense, Michael.
That's a good point. Yeah, I guess
So-
the algorithm does currently run dynamically. There's no feedback. So I would have to like that doesn't exist yet. I could add
Mm.
portions that say, like if you remember the bitmaps, right? That's kind of all baked into the code. And so I could just say no solution, but hey, here's the bitmap of maybe like a couple options, and then you can kind of just work with that. But yeah, that's a good point.
Well, awesome. Hopefully you have a beefy future work section, because I think this is promising, and we have a project where we're trying to build a exhibit. We want to build a real exhibit around the oil rigs off of Santa Barbara, and we have a physical space, but we want to reproduce it in virtual reality to make it mobile. So I would like to make that experience less nauseating. So it would be interesting to see if this could help. Like we could set up room in our lab to test walking through the exhibit virtually, with your algorithms guiding the turning of the player. And so anyway, I just think it's interesting to keep pursuing. Like,
Yeah.
hopefully, yeah, it can live on.
Cool. Yeah. Yeah. Just one thing to add is that one thing that my presentation doesn't try to go over is if you remember, like kind of the Unity demonstration says, oh, if these tiles aren't reachable, we kind of just remove them. But one thing you could do is you could append to it. So if there's an offset down, instead of just removing what's not reachable, you can add to your virtual environment. So if you're just doing something like surveying like a real place, and it's not like a game, right? You don't need to make it challenging. You could always have 16 tiles available, if that makes sense. So you could use that too.
Excellent, thanks. I look forward to reading it as well, and I'll do that soon.
Yeah.
And get you any feedback within 24 hours, or you could just ignore my feedback because I didn't get it to you in time.
Appreciate the honesty.
Yeah, I'll be sending a version of the paper with like some notes on it as well later.
Awesome. I appreciate that. I'll read into that.
Okay, then I would like to ask you, Chase, to stop recording, because now comes the part where I make a breakout room and go with April and Michael into the room, and we'll deliberate